musunuz?
Much smaller than the internal. And therefore, the effect of Zeeman is going to be smaller than fine structure. So really, when you look at this line, and you have the first two terms, you should think of these two terms as your long Hamiltonian. And the Zeeman term as its perturbation. Yes, we've solved for the fine structure couple and the shift. So this is the known thing. These are going to be the known states with known energies. First order, but you know them. And then the Zeeman effect will be the perturbation theory on this. This is the weak Zeeman effect. How about the strong Zeeman effect? So B strong. This time the magnetic field associated with the Zeeman effect, external magnetic field, is much smaller than the magnetic field responsible for a spin-orbit coupling. And this time, what are we going to do? Well, we'll think Hamiltonian to the H0. Strong Zeeman effect means this Zeeman Hamiltonian is a lot more important than the spin-orbit coupling, so we'll add delta H Zeeman here. And we hope this will be our known Hamiltonian. Because anyway, the Zeeman stuff is much stronger now than fine structure. So this should be our known Hamiltonian. You should complain, no, this is not known. I haven't done Zeeman, but we'll look at it. And once we have our known Hamiltonian here, spin orbit has to be rethought. Fine structure has to be rethought as a perturbation. So, case A, quick Zeeman effect. So what are our states here? We discovered that, and we know those are the coupling basis states, and the states of H0 tilde, eigenstates, or eigenstates. Approximate eigenstates are the states of J and J, and the energies were energies independent of N and J. We had 1s 1 half, 2p 1 half, and 2p 3 halves. Roughly, to remind of what happened, the original states were shifted, and we used the J quantum number in here. And those are our multiplets. Those are our multiplets, and we have a lot of degeneracy as usual. So this is degeneracy here and degeneracy here. Because a multiplet P3 halves is J equal 3 halves, and at here states. Here you have two states, and here you have two states as well. So particular states that are degenerate. So in principle, when we do the Zeeman splitting, we may have to consider the full matrix M, L, J, M, J, delta H, Zeeman, and L prime J, M prime J. So what are our degeneracies? Our degeneracies are when you have a given value of J. So a degenerate subspace can have different L's, for example here, of the same J, and therefore different MJs, or within a so this is the scope of degeneracy, and in principle we may have to diagonalize things like that. Degenerate spaces, if we're doing the level 2, we would have to discuss this 4 states here, we would have to discuss these other 4 states. Happily, we don't have to do that much, because, as usual, the delta H Zeeman is proportional to LZ plus 2SZ, and this commutes with L squared, with delta H Zeeman. L squared commutes with any L operator, it certainly commutes with any S operator, they don't even talk to each other. And therefore, L squared commutes with L Zeeman, which means that when L is different from L prime, this matrix element has to vanish. This is our knowledge from perturbation theory long ago. We have another operator from which the states have different eigenvalues, complete with the perturbation, and the matrix element of the perturbation must vanish between those states. So we don't have eigenstates like that. And when L is equal to L prime already, so we focus on L equals to L prime. So we only need to worry within multiplets. So we have N, L, J, MJ, delta H Zeeman now, N, L, J, MJ prime. It's an issue of MJ prime now. But Zeeman thing commutes with JZ. JZ commutes with delta H Zeeman. JZ is LZ plus SZ, and Z components in angular momentum, two identical components always commute, of course. So JZ commutes with delta H Zeeman. So this thing will vanish unless M is equal to M prime. And that's great, because we're back to the non-degenerate perturbation theory. The whole matrix, this Zeeman thing could have turned out to be complicated matrices. No, it's perfectly diagonal in this basis. There's nothing to worry about here. Except that it's still not easy to compute, as we will see. So what do we need to compute? We'll have the first order corrections due to Zeeman on the N, L, J, MJ basis. Is equal, well, Zeeman will have an E over Z, so let's put it there. Let's put the B close to the E to MC. And now we have N, L, J, MJ, LZ plus 2SZ, N, L, J, M. MJ. Diagonal. And that's non-degenerate perturbation theory, because all the energies we want, all the splittings we want. So basically what's going to happen, as you can see here, is that the things don't mix everything. There's two levels of the split. There's two levels of the split. There's four levels of the split. Everything is in the split here. The remarkable thing of this formula, and it's going to keep us busy for about 10-15 more minutes, is that this thing, this matrix element, is proportional to MJ. So the state split proportional to the M1 number of the state, and the 3 halves was 3 halves as much as the state equal 1 half. And that's not obvious here. It's a remarkable result. It's part of what's called the Wigner-Eckart theorem, something that we studied well in mathematics. We're going to see at the beginning of it in this computation. And it's a fairly remarkable result. So the remarkable result here, remarkable, is that E1s are proportional to MJ. And that defines a linear splitting, because it's linearly proportional to the magnitude of the magnetic field and divides the states nicely. So we want to understand this matrix element, and there's a little thing we can do. Notice that LZ plus 2SZ is equal to JZ plus SZ. You can take one of the SZs and complete JZ, and you're left with that. So the matrix element NLJM, LZ plus 2SZ, NLJMJ, is equal, you have a JZ, that gives you just something proportional to HMJ, plus NLJMJ, SZ, NLJMJ. So, okay, a little bit of a mystery maybe seems to you at least consistent here. I said this matrix element turns out to be proportional to MJ, and certainly this piece having to do with the J components here is proportional to MJ. This one, this matrix element will be proportional to MJ. We will verify to some degree in the homework on Wednesday of vector operators. This operator, SC, the one-line summary for this operator is a vector operator under angular momentum, under total angular momentum, and as such, those matrix elements will be matrix elements of JZ. So how is that so because if you say that S is a vector operator under J, this will say that for J, S is a vector. And that is a complete statement. You should check whether it's true. It's stated that Ji is Sj, hence I and J1 from 1 to 3, is equal to I H bar epsilon I Jk Sa. That is a statement that S is a vector operator. You may have seen this in a previous course in 805, where we might have proven that X and P are vector operators for L. And here the proof is not all that difficult. In fact, it's almost obvious this is true, isn't it? Ji is Li plus Si. Li doesn't talk to Sj, but Si with Sj satisfy the algebra of angular momentum that is precisely this one. So this is almost no calculation. You will check and remind yourself that you have a vector L for L, X and P are vector operators. So for example, Li Pj is I H bar epsilon I J K Pk. And This you do by calculating the commutator, but after you calculate the commutator a few times, it's better to just remember, oh, it's a vector operator. That's a good way of thinking about this. Okay, if you have vector operators, they have a very peculiar property sometimes. One that may sound a little unmotivated, but it's very useful, is the following. Suppose you form the double commutator of j squared with the vector operator s. Here you will find an identity. To make it fun for you, I will not tell you the number that appears here. It's some number. But with some number here, this is identical to the following. S j times j minus 1/2 j squared s plus s j squared. Well, it's important to look at this equation even to make sure everything is in order. This is a vector equation, so it's 3 equations. So j squared, despite all this arrow, is a scalar, has no indices. It's j1 squared plus j2 squared plus j3 squared. S, on the other hand, has an arrow, and it's a vector, so you could look at this equation for the third component, for the first component, for the second. So here is a vector with 3 things. Here is also a vector, it's s dot j and j. So the vector index is carried by the j here. The vector index is carried by the s here. Once to the left of the j squared, once to the right of the j squared. Also, maybe you should notice that sj is the same thing as js. Not because this operator is domain, because sx and jx is y and j and suz and jz different components of the algorithm. This one's the commute. So this is a formula you will show by computation. I don't think there's a simple way to derive this formula, but it's true and follows by computation. This formula implies a result that is sometimes called a projection lemma. So this is all the points trying to pick a matrix element, and we're forced to consider a lot of structure. Just trying to show this simple matrix element with an S j. So suppose define its expectation value of this is an eigenstate of j. So suppose we have j and a state is an eigenstate of j. Now let's take the eigenstate value of now look at the left-hand side. It's a commutator. You have a j squared on the left, a commutator on the right, minus a commutator on the left, j squared on the right. In both cases, there will be either a j squared near the right or a j squared near the left. Those two terms come with opposite signs. Since those are eigenstates with the same eigenvalues, that's what we're doing, an expectation value here, the left-hand side is 0. So the left-hand side contributes nothing. So left-hand side is 0 on this thing. 0. And let's look at the right-hand side. It's equal to j mj s dot j mj and minus. So that is the first term. Now we have to compute this thing on this jm state. Again, a j squared is either to the left or to the right. Therefore, this gives a number, which is h squared j times j plus 1. This gives the same number associated on the right. You have 2 terms. The factor of 1/2 cancels, and you're left just with the expectation value of s, which is kind of what we wanted here. So this is minus h squared j times j plus 1, which is the expectation value of j squared, times the expectation value jmj of s on the jmj. Okay, you have this term minus that term equal to 0. So what have we learned? We have learned that this term, that we can call the expectation value of s vector on a j eigenstate, is equal to the expectation value of this quantity, s dot j on the eigenstate, divided by this number, which turns out to be the expectation value of j squared on that eigenstate. This formula looks like a projection formula, in which you say the expectation value of s is the expectation value of the projection of the vector s onto the vector j. Remember, if you have, for example, projection of a vector a into a unit vector n, what is the projection of a vector a into a unit vector n? Well, the projection is a dot n times n. That's the component of a along the vector n. But if n is not a unit vector, the projection of a along b is a dot b times b over b squared. Because, in fact, the projection along a vector or along a unit vector is the same thing. It's just a projection. And here you have solved. It's conceptually interesting. It's valid for any vector operator under J. And this will answer our question, because now we can use this for examples. So what do we have for our case? We have that N, L, J, M, J, S, C, N, L, J, M, J is 1. Well, we have expectation value of JC on this case, so it's going to be H bar mj over H squared, J times J plus 1, that's the denominator. And you still have here what may look like a small challenge, or a big challenge, it's a small challenge, S dot L N L J M J. Here, this is called the scalar operator. This is invariant for coefficients. So as scalar operators are independent of MJ. We got the MJ dependence here. We want to claim that this expectation value is proportional to MJ, and we have the result here unless there is MJ dependence here. But there's no MJ dependence here because, as I said, this has to do with the fact that this is a scalar operator. So let's calculate this part to finish this whole computation. How do you do that? Well, you have to remember you have J equal to L plus S. So, here, we'll do the following. I'm sorry, I had the confusion here. S dot J is S dot J here. It's starting to look wrong. So I need the dot product of J and S. So here, I'll take L equals to J minus S. And L squared is equal to J squared plus S squared minus 2 S dot J. Here is important that S and J, S dot J and J dot S are the same. And therefore this S dot J is 1/2 of J squared plus S squared minus L squared. So with S dot J being this, you see immediately that is this number. This is H bar mj, H squared, J times J plus 1. And now, 1/2, so I have a 1/2 here, I'll put it from J squared, so this is J times J plus 1, there's an H squared, this is in addition, H squared here. J times J plus 1, S squared, which is 3/4, so 1/2, minus L squared, which is minus L times L plus 1. Okay, almost there. This is time. Have our result. So what is the result? The matrix element N, Lj, Mj, Lz, oops, Lz plus 2SC, back to the whole matrix element. Remember we had one piece, HMJ, and now this part. So adding the HMJ to this new part, we have HMJ 1 plus J times J plus 1 minus L times L plus 1 plus 3/4 over 2J times J plus 1. Okay, I'm sorry, it's all here. I just copied that term, hopefully without mistakes. So we have our matrix element, and that matrix element